Welcome to Transportation Management. This week we'll cover part one of this very key topic, and transportation management is key because, as you might remember from module 1, transportation costs are often the biggest part of logistics expense. If you look at the total logistics expense, either transportation or storage are the two biggest chunks, and one of the two is usually the largest. Often transportation is a little bit larger than storage expense or warehousing inventory type of expenses. So transportation management has to do with providing reliable transportation for your organization according to its needs at the lowest costs. Okay, so at this point you already should understand 5 modes of transportation, or the 5 common modes of transportation, which are air, trucks or motor vehicles, sea, which is rivers where you have some barges that go, or oceans, ocean freight. So you have air, truck, sea, then you have rail, and then you have pipeline. Okay. Now, if you think back to when you studied those modes, you might remember that trucks and pipelines are the only modes which go door to door. So pipeline might go from an oil field to an oil refinery, it's door to door, or for some purpose, in some cases it may not go door to door. You may have oil tankers to carry the oil to some other facilities, but pipeline can be door to door for large facilities. Trucks are door to door for large or small facilities, and other than that, rail, air, water, they're all not door to door. They have terminals or stations, and then vehicles or equipment move between these stations, and then you have to get them from the station to your facility. So that's where intermodal transportation comes in. Intermodal means you combine any of the other modes with truck, because trucks excel at door-to-door service, so you can provide door-to-door service. So if you want to ship something fast with air, you're going to combine air with truck to get what's called birdie back, so that you can pick up things from the door of the sender, take them to an airport, have them fly the line haul, the long distance, to another city or another place, and then take another truck and then deliver it to the door of the recipient. So that's called intermodal, because you're combining 2 modes, truck with air. You can also combine truck with rail. That's called piggyback, probably because rails are slow and pigs are slow. And then you have truck and water, fishyback, and then you could have truck and pipeline. Now you can obviously combine, that's not the only combinations possible, right? You can also combine rail and air, for example, or rail and water, for example. So sometimes you might see that there's a port, and when ships come in, freight comes in over the oceans to the port, then there's a railway station on that port, and you load the stuff from the ship onto rails, and then the rail goes forward. So you might see that, for example, if there's a coal power plant and you're importing coal from outside, it might make sense to set up a railway line from the port to the coal power plant, because coal is low value. You want cheap transportation, and in that sense it makes sense to have cheap rail transportation from the port to a coal power plant. So you're going to use up a lot of coal over a year, right? So there are situations where rail plus water or rail plus air also makes sense, but the most common ones are birdie back, piggyback, and fishyback. Now, when we do intermodal transportation, we have a huge problem. The problem is that unloading and loading is going to happen multiple times. So if you're combining rail and truck, you pick up stuff from the sender. So you load up a truck, then you go to that railway station, you unload the truck. So you have loading, unloading happening twice already. The unloaded truck will then get loaded onto a rail car, right? So that's a third activity. Then the rail car will go to the destination station, where the rail car will get unloaded. That's 4, right? Then the truck will get loaded on the receiving at 5. Then this truck will go to the destination and unload its stuff at the warehouse 6. So you have 6 operations, 3 loadings and 3 unloadings, instead of just 1 loading and 1 unloading. So instead of 2 operations of loading, unloading, you go to 6. So 3 times increase in what we call materials handling cost. Okay, and materials handling cost is the cost to unload, offload, move material. And actually it's going to be more, because when you go to a railway station, the train might be parked at some distance from where the truck is going to park. So you may have, when you offload the truck, you may have these smaller trucks or other equipment to carry pallets or boxes, over to the railway line and then load up the rail car, or you may have big cranes doing that, something like that. So you're going to have some equipment expense, some labor expense, time expense to do all these loading, unloadings, which made intermodal transportation so expensive, because the savings you're going to get from using rail over the line haul, some of those savings will be taken up by this 3 times or more increase in material handling cost. So to solve this problem of material handling multiple times in transportation, a container was invented. Containers have changed the world because they have made trade cheaper, transportation cheaper, and so a lot of times transportation and trade makes sense now with containers, where it was rather expensive in the past. There's a very interesting book called, I believe it's called The Box That Changed the World, which is about the history of containers, how things were done before containers, how expensive that was, and how containers became popular and were standardized, and how things are easier now and cheaper now with containers. So what is containers? A container is just a box, often a metal box. Yeah? So it's a box. Some people consider it to be a must in intermodal transportation because it cuts down on that loading, offloading, all of that activity, and saves you money because you don't have to do all that activity. It's reusable. Okay, so you pick up the container whenever it's delivered, and then you take it back and you fill it again, and so forth. Yeah. You can seal it, so nobody opened it on the way. So it's a metal box, so it's kind of secure. And the most important part is, because it's a standardized metal box, a lot of cranes and trucks with this big arm, often with a big magnet on top, can pick it up, or they could have prongs to pick it up, and you can pick up the whole container, move it somewhere else, and pluck it down. So you could offload a vessel, a ship really quickly if it's loaded with containers. You could offload it onto trucks quickly, truck to rail. Any of these movements, the loading, unloading is very quick, very efficient, because you just pick up a container and put it somewhere else, and these are pretty large. Okay, so what are the advantages of containers? This is a very important slide, because you should have this in your mind, that why are they so popular and so used so widely. So they reduce theft, damage, and multiple handling costs and intermodal transfer times. So not only do they reduce material handling costs, but they also reduce the transportation time, because the time spent offloading and loading is reduced drastically. They're waterproof, they can be airtight, or the standard ones I believe are airtight. They can be locked, sealed, stacked on top of each other. You don't need any shelving to put containers in. The container is strong enough to support the weight of containers on top of it. So you just stack them up like pieces of blocks or Lego. They change material handling costs from labor intensive to capital intensive, because you can't have people go around and lift up a container, it's too heavy, and so you use these cranes and other machines to move containers around. But once you make that investment into equipment, it reduces your variable cost of material handling a lot. You can also get refrigerated containers called reefers. So if you want to ship milk or ice cream or medicines which need a certain temperature, you could have a refrigerated container which can keep things cool inside. Okay. International standards, there's more than two, but the most popular two sizes, which are international standard sizes, are called the TEU and the FEU. The TEU is called the 20-foot equivalent. The dimensions on the are 20 foot by 80 foot by 8.5 feet, and the 40-foot equivalent is 40 feet by 8 feet by 8.5 feet. Okay. You would notice in these two that the two dimensions at the end are the same. The only difference is one is twice as long as the other, which is where the name comes from, 40-foot and the 20-foot containers. Okay. Inside the US, you can use bigger containers because US law allows for domestic transportation. You can use a 53-foot container, which is 53 foot by 9 foot by 8.25 feet. So locally, you might use a different size containers. Now, sometimes, depending on the carrier, you may even be able to transport internationally on this container size. This doesn't mean that nobody else uses it, but these are the standard international ones, and these are, you may have to check with the carrier if they can take care of this container outside the US or not. If you look at the weight limits, you see an interesting pattern. So 21,000 kg or 21.8 tons. 1 ton is 1,000 kg. You can maximum weight limit for a 20-foot container. You double the volume, because this is 2 times 20, so 20 times 8 times 8.5 is the same volume as TEU. 2 times that, this is twice the volume. So you go to double the volume, but you don't go to double the weight. You only get maybe 5 extra tons. Here you increase the volume a lot more compared to a TEU, but you get less weight than TEU. Okay. Okay, so why are these weight limits? They don't make sense. There have to be several factors. So here, for example, in domestic shipments, a lot of these shipments go by truck on roads, and so there's a limit on how heavy a truck and trailer combination can be, and so you can't just put a very heavy load, go over the roads and destroy all the roads. So other considerations like that. In addition to, the engineering aspect, if you have a huge container which is very heavy, a slight tilting or slight movement in carrying it can lead to a lot of moment either way, and kind of make the container fall, or you need to have it can increase the requirements of the equipment which can carry it and so forth. So lots of considerations which they have looked at to come up with the weight limits. What this means is this: if you have something very dense and heavy, you might be better off putting it in a TEU, because you can have a lot of weight for little volume. And it's going to be cheaper than an FEU because it takes less space on a ship. FEU might be better if something is not very dense, so it takes up a lot of volume but doesn't have a lot of weight. Because if you were to pack that thing in a TEU, the volume would get filled up and you would be nowhere close to the weight limit, right? So, depending on what you are shipping, you pick one or the other. So you should remember 2 terms that people use: weighed out or cubed out. So as you load a container, let's say the container is not full, you can see empty space inside, but the weight limit has been reached. Now you're weighed out, you can't load anything else on this container because you would then exceed the weight limit, even though there's space in it. Right? There's physically the space there, you could put something else in, but because you're weighed out, you've hit the weight limit first, you're weighed out, you can't load anything else. Cubed out means you hit the space limit first. So you're loading something and the container becomes full, right? And now there's no more space to put anything else, but you've still not hit the weight limit. Okay, so that means you're cubed out, you've run out of cubic meter or cubic feet space to put more stuff. So if you're transporting something like mattresses or pillows, which take a lot of space but are not as weighty, the FEU might be better, because with TEU you'll get cubed out really fast. You'll fill up the volume and you would have used very little of the weight limit. With FEU, when you get cubed out, when you have used up all the volume, you might be closer to the weight limit than you would have been at a TEU. With a TEU, right? So you can do these calculations for a given container. How much product can I load? Keeping in mind that you cannot just divide the weight limit by the weight of the boxes. I've actually seen this happen where, I tell somebody, okay, you have a box which weighs 10 kg, how many boxes can you load in this container? They divide this by 10 and they say, I can load 2, 6, 6, 8 boxes in this container. No, you have to look at the dimensions of the box. What if it's a huge box and you can't fit that many boxes in this much space? So you have to always think about the volume and the weight together. Which limit do you reach first? That's your capacity for that container. Okay? And then once you figure out how many boxes or things you can load in the container, then you can take the price of shipping the container, right? How much it costs you to ship one container, divided by how many boxes or items you could pack in it, and you would get, what's the transportation cost per unit or per piece. Yeah? So you might get a question in the homework or the exam where you have to calculate the transportation cost per piece. You're given the volume and the weight of one unit. Then you have to pack up the container to see how you can pack it up, right? And then because you might get cubed out first or you might get weighed out first. So you don't just divide the total weight capacity by the weight of your box and say, I can load this many boxes. You have to look at the volume side of the equation as well. This is a picture of a container. I think most of you might have seen a container already in your lives. If you have not seen it, that's what it looks like. You can see there are doors here which can open. You can put a seal here, lock here, things like that. You can see the corners are a special type with these hole and the special type of corner, because the picking equipment will sometimes lift from the corners. So they are kind of standardized. The corners have to be that way. Okay, this is a container that is full of boxes of product. Notice what's going on here. There are no pellets. Pellets are these wooden, often wooden, they could be plastic or metal as well, often wooden, kind of like a flat shelf with 2 levels, a gap in between, where you can insert the arms of a lifting truck. Okay. So if there were pellets here, you bring a lifting truck, insert the prongs in the pallet, pick up the whole pallet, move it out. Then you go pick up the second pallet, move it out. And you may have 4 or 5 boxes high on each pallet. So this could be 3 pallets vertically or 2 pallets. Now pellets make offloading and loading the container really fast. Once the container is loaded, you just pick up the container from a truck, put it on a ship, things like that. But first you have to load up the container, and pallets can make loading, offloading the container really fast. But pallets also take up some space. So if you put 3 or 4 pallets here, you might lose 3 rows of boxes or 2 rows of boxes, because that space is going to be used up by the pallets. So here the trade-off is loading, offloading cost versus how many boxes you can ship in one container. And this company decided that the loading, offloading cost is not very high, and we rather use up the space and not waste space with pallets, use up all the space for our cartons. That's again a calculation you can do. You can see how many boxes will you fill up if you use pallets, how many boxes can you fill up if you don't use pallets, and then what's the savings in time and cost of loading, offloading a container if you use pallets versus you don't use pallets. Okay. By the way, there is newer equipment that can automatically offload this, like with a robotic arm, even if you don't have pallets. So you might need to offload, maybe the first row manually to give it some space, and then the arm will go in and keep picking up one box at a time and offloading it onto a conveyor belt. So some advanced warehouses may have this container come in, and then a robotic arm offloads the container, even if there are no pallets. And that's the best of both worlds. You used up all the space for your product, you don't waste any space, and then offloading, loading is automated and relatively cost free, only the cost of electricity to run the robotic arm to offload this thing. This is what a reefer can look like. So you can see it's called reefers here. So this would carry something that needs the temperature to be controlled or frozen, like frozen goods. Now remember that for a container, what is standardized are the corners and the weight. So nothing can go outside the 4 corners. But within the 4 corners, you can have a tank like this. This is a standard container. It doesn't have to be a rectangular box. You have a tank as long as the corners are standardized and the weight is standardized, right? So this, for example, could be used to transport milk or other fluids. This is a port. You can see this is a ship or a barge that's docked onto the port. You can see these arms of the crane. Along each arm, this piece moves, the arms can go up and down, and this piece can go this way and that way. So this will pick up a whole container, come this way, come down. There'll be a truck parked here onto the truck. The truck drives on, this will come back up, go here, pick up a second container, and so you pick up one container at a time, which is very quick offloading and loading. This is, you could say this is the storage area of the port, just an empty, like a parking lot where you can stack up containers that are waiting for somebody else to come and pick them up. Or this could be an area where customs do their inspections and stuff. And so you could have these, a carrier truck type of things. They also have this big arm at the top. See, it's connecting to the four corners like that, and it's picking up the container to move it around inside the port or the storage area. This is the offloading. So this crane like this is the offloading part. You can see the containers are picked up, okay, and you could have trucks drive under them, and these arms could just place it right on top of the truck, and the truck drives on. Here you can see that happening. So you can see this truck is parked in the right spot, and this container will get on the truck. There's a second truck waiting for its turn. As soon as this truck drives on, the second truck comes in. When that drives off, the third truck comes in. So you have these trucks coming in a line, and each one is getting plucked up. Each one is getting a container plopped onto it. Okay, let's look at an example of mode selection where we have truck or air. This will probably be birdie back. You'll have trucks at the end of it, and you have piggyback, which is rail plus truck. Okay, obviously rail is the cheapest, truck is more expensive, air is very expensive. Okay, obviously air is going to be the fastest because above 500 miles air is the fastest. Truck is going to take 5 days, rail is going to take 14 days. This is the lot sizes. So the truck is big enough. Maybe you're using a 35-foot container on a truck. It's going to carry 35,000 of your product. So you have boxes. It's going to carry 35,000 boxes. Air, the unit that you ship in is in a different shaped box for air cargo. If you look at the cargo hold of a plane, it's not rectangular. So you have a box which has like these sides which are not really rectangular. And so for that box or that unit of transportation for a plane, you can fill in 17,500 of your units of product. Rail car is a huge rail car. We can put in a lot of product in. Okay? And then the transit time, which is door to door, D to D means door to door. Right? So this is not just rail. Rail might take 12 days. Then each end you have 1 day by truck. The total time is 14 days. And then you have some standard deviation, which means that if they say 14 days, they could take 20, they could take 10. It's going to be variable. And how much variability you have, this is the standard deviation that tells you that. So you want to ask yourself, well, which is the cheapest mode? If transportation costs were the only thing that mattered, you take the transportation rate, multiply it by your annual demand, how much you're going to ship per year. Okay, my annual demand is 700,000 units. So I do 700,000 times $0.12 per unit, okay, to get the transportation expense if I use piggyback. And I do the same thing, 700,000 units per year, annual demand, times the transportation rate to get my total annual transportation cost using truck. Same thing for air. And you would obviously notice rail is the cheapest because these numbers times 700,000, the smallest cost is going to come from the rail. 0.12 times 700,000 is going to be the smallest annual total cost. However, because rail is so slow and so variable, it's going to increase your inventories drastically. So you have to not just look at the transportation annual cost per year, you have to also factor in the inventory cost per year by using rail, and then look at the total of inventory plus transportation cost across the three modes to see which mode is cheapest on total cost. Remember, we always take the system's perspective. Don't just optimize one part of the system and say you have the cheapest transportation. Look at the whole and look at the cost implication for the whole, which means you have to factor in the inventory part as well. Okay. Now I'm not going to go over all the details. The details. There's a separate lecture on how inventory costs are calculated, which goes over the detailed calculations for inventory, and you can put the numbers in your workbook to do that calculation. Okay. But this is an example. Try to do this calculation yourself using Excel, and then compare your numbers. You should be the numbers I'm going to show you next, which are the costs. Your numbers should match those numbers, and that way you know how to do this. If you don't know how to do this, go back, look at the inventory cost calculation lecture. Okay, so here I'm showing you the detailed steps. You don't have to worry about the detailed steps. So in this example, our lead time is just the transit time, because when we are, there could be two reasons. One, we are assuming that it's the same supplier. So when you place the order with this supplier, whichever mode you choose, if the supplier takes 5 days or something to process something, and then the shipping time is the transit time, or the transport time is the transit time, the only difference between the modes is because of the transit time, not because of the lead time. That's constant. Okay, and so we can just look at the transit time. The other could be that the supplier has the products in stock, and so when you order, the supplier immediately ships them, and so the transit time is basically your entire lead time. Now notice that sometimes you have scheduling issues. Okay, so the flight doesn't go every single day, or the train doesn't depart every single day from the supplier's city. So in that case, if you are going to be ordering at any time possible, you have to look at the average waiting time and add that to the transit time. So on average, if you wait 2 days before a train departs, you'll add that to the transit time, because if you were not using rail, you were using truck, you would not be waiting those 2 days. Okay, so all that is already added in. So in this case, the lead time is the transit time, because we're just comparing the transportation aspect. We're not comparing suppliers, which may have different lead times. We're just going to compare these options on transit time. Okay. So lead time is T, the transit time, and the transit time is also just T, the transit time. So here lead time will be 14 days, and for pipeline inventory cost, the transportation time will also be 14 days. If you want demand per day, you can divide the annual demand by 365 to get demand per day, which you might need to do. Why? Because the times are in days, and the standard deviation is also days. So you want the demand to also be in days with the standard deviation and so forth. So you can see the daily demand is given here, 2243, and standard deviation of daily demand is 500. So you'll work on the time unit of days for all the calculations. Okay. This formula should be familiar. Again, if it's not, the details are explained in the inventory cost calculation part lecture. Okay. So when we look at the final numbers, we get transportation expense. As we expected, the piggyback, it should be back, not bank, piggyback, which is the rail, is the cheapest. The truck is more expensive, the rail is the most expensive, just on transportation cost. When you factor in the inventory costs, rail becomes really expensive. Look at the inventory carrying cost, much larger compared to truck and air. Okay. Look at the stockout cost. You're going to have more stockouts with rail than with the more reliable forms of transportation. Less stockouts, more stockouts here. Okay. Look at the transit inventory cost. So if you own the inventory during transit, you're going to incur this cost. Rail takes a long time, a lot of cost. Truck and air take much less time, much less cost. So in total, when you add the inventory cost and the transportation cost, this is sometimes called the total relevant cost. This is the total relevant cost for this decision on which mode to use. If you went with rail, annually you'll spend this much money, dollars per year, on inventory and transportation to use piggyback. Annually, you would spend this many dollars per year. Every year you spend this many dollars. If you use truck, some of these dollars go to transportation, the other dollars go for inventory and storage. And air is above $1 million, so it's really expensive. Okay? Because even though inventory costs are really low, the initial transportation cost is so high that you never end up saving enough in inventory in air. So a net truck, even though it's more expensive on transportation rate basis, ends up being cheapest overall amongst the three modes in this example. So you could use the same logic to compare different transportation options or modes. Okay, let's go to the second part of our. So that was all for intermodal, right? So we started talking about intermodal. Why do we need to do intermodal? How containers help with intermodal, and how we can compare different modes using a total of transportation and inventory expense. Now we're going to move towards route selection. Okay? So because the first decision in transportation is you kind of have to think about which mode you're going to use, right? Am I going to be shipping this product from these suppliers by air or by truck or by rail? Once you have a mode in mind, then you might say, okay, if I'm going to use rail or truck, there are multiple ways it can get here, right? I could use this railway line, or I could use this one, or I could use this truck, or I could use this combination. And so now we're going to look at how do you select which route to take, so that how this stuff actually moves from the source to the destination. We're going to do an example to illustrate the logic that we use, and then you can use the same logic in your own decisions. We have a supplier in Shenzhen, China. So this is the eastern part of China. Shenzhen, China, somewhere here. We want to move product from that supplier to our warehouse in Kansas City, USA. Okay. Okay, so this journey is going to have three parts. First, because our supplier is not located right on a port, we're going to have inland origin transportation. Inland means overland, origin at the origin country or origin site. So that's going to be from the door of the supplier, the origin door, to the origin port. So Shenzhen, the supplier's door to the Shenzhen or some port in China. Okay. Then we're going to use water for the port-to-port transportation, or the line haul part. This is the line haul from port A to port B to some port in the US, from some port in China. And then we have inland destination, which is from some port in the US to the warehouse doors in Kansas City, USA. Okay, so three parts of our journey. Now I have kind of drawn a straight line on the picture, but you should remember that if you're looking at a two-dimensional map, a straight line between points A and B is not going to be the shortest distance on a two-dimensional map, because the Earth is not two-dimensional. Okay, so the Earth is what we call oblate spheroid. Basically, take a sphere and you squish it a little bit. The kind of shape you get is what is approximately what the Earth is like. So the shortest distance on the surface of the Earth is going to look like a curve on a two-dimensional map, which is why if you see those airline flying patterns, you often will not see straight lines. And so you might wonder, why are all these airplanes traveling in curves? Well, they're taking the shortest distance on the surface of a sphere or an oblate spheroid, and that shortest distance on a two-dimensional representation looks like a curve. Okay, so let's look at the first stage, which is the inland origin part of the transportation. Okay, so if I look at the city Shenzhen, okay, I can see that there are a few options close by. Okay, I have a port in Yantian, I have a port of Hong Kong, And I believe there are bridges connecting Hong Kong to the mainland, so you could have a truck drive over the bridge. Because you might wonder, well, how am I going to take a truck from here where there's like water between them? Trucks don't go over water. Well, we have bridges here, so you could actually drive by truck all the way to the Hong Kong port as well. Okay. And then you have an airport, Shenzhen Bao'an Airport. And so the first option is, are you going to send by air? You might use the airport. Are you going to send by water, ocean freight? You might use one of the ports. And we have already made the decision. It might be obvious in this case, if you're shipping shoes or something like that, that air is going to be way too expensive. We're going to go by water in this case. So we're going to ignore the airport. We basically have two options. Okay. Now from port to port, we have these routes that this ocean freight can take. Okay, this, for example, is data from the APX Atlantic Pacific Express. You can go to these ocean freight transporting companies or carriers and look at the routes that their ships take and what's the schedule. You'll get which port city, okay, which day of the week, you're going to depart and so forth. Okay. So we can see that we can start at the Hong Kong port. We're going to pick up more stuff from Taiwan, South Korea, Japan, and then we're going to go over the Pacific. Okay, I believe this is the Pacific here. Between the west coast of the US, east coast of China, there's the Pacific Ocean. So we go over there. Okay, then we go here through the Panama Canal, and we can hit any port on the east coast of the US. You could hit Miami, Jacksonville, Savannah, Charleston, New York. You could drop off your load here, here, here. You could tell them where you want the load to be dropped off. The transit time would vary, so depending on which ports you pick, you can figure out what the transit time is. For example, here, you're going from Hong Kong to Miami, that's 28 days. But if you go Hong Kong all the way to New York, that's 33 days. You get 5 extra days from Miami to New York, depending on where you want to offload your stuff, and then you're going to take a truck from then on. We have another option. Okay, this one actually, this CSCL America Asia South Loop is going to actually hit the Yantian port, and then it's going to go hit some other ports and go to the west coast of the US, and it's going to hit, I believe, the LA port, Los Angeles. Okay. Then for the last stage, okay, you're either going to arrive on the Los Angeles port using the CSCL freight, the ship route, or you're going to arrive somewhere on the east coast at one of these ports using the other carrier. Okay. So from these ports, what options do we have to get our product to Kansas City? So we can take rail or truck. Okay. So for example, from New York, New Jersey to Kansas City, truck may take 2 or 3 days. Rail may take 5 to 12 days. With intermodal, there's going to be rail with trucks to do the intermodal part, so it's going to be rail intermodal. A lot of railway carriers are going to give you intermodal options where you don't have to worry about where the train station is. They'll link up with a trucking company to give you transportation. And you can see, in this train, see the containers loaded up here. So these were probably picked up at some port by a truck, loaded onto the rail, and they'll go to another railway station, then use a truck at the end again. And there will be other options too, right? So you could list all your options. Okay. So here we have 2 ports in China to use. Okay. The cost per container to take from our supplier to the port is given here. Okay, and then each of the ports, the container is going to wait for 2 or 5 days for processing, customs checks, and then the schedule of the transportation. The ocean ship is not going to be leaving every day, every hour. You may have to wait for it. So all that combined is 2 days on average, 5 days on average. Then port to port, we could go to LA, which is $1,100 per container, 20 days. Now these numbers may have changed, right? You can get the up-to-date numbers online. So this is just an example. Don't hold me to these exact numbers. I'm just trying to show you the logic behind the decision. You could go Hong Kong to LA, a little bit cheaper, 1,025, 13 days. Okay, also faster. You could go Hong Kong to New York. Okay, and then at the port, if you pick the LA port, 5 days. New York port, 3 days to process the containers and load them onto the next transporter. And then inland, you can go LA to Kansas City by rail, intermodal. You go New York to Kansas City by Norfolk Southern, rail, intermodal. Or you could go by the truck, and you have the cost and the time for all of these days. So a good way to represent all of this information into a form where we can look at it and analyze it is to make a network diagram. Okay, sometimes called a transportation network diagram or operational network diagram. I'm just going to call it a network diagram for simplicity. So if a question tells you draw a network diagram, it looks kind of like this. The circles are places. So SZ is Shenzhen, Hong Kong, Yantian Port, LA Port, New York Port, Kansas City. This is our facility here in Kansas City. The lines connecting them represent transportation. Okay, so each line which connects two circles is going to have a cost in dollars and a cost in time. So going from Shenzhen to our supplier's facility to the Hong Kong port costs 5 days in time and $30 per container. Okay. Now you might see a cost number and a time factor at the ports, because the ports may have their own fees that they charge you if the fees are not included in the carrier fees here. And the ports also take time. So you can see that the New York port takes 3 days, LA port takes 5 days, and these ports also may have some time associated with them if you have not factored in the time here. Sometimes people put the time at the port here into this path here, but I would prefer you put the time here on the port itself. Okay, and all the way to Kansas City. So if I was to take the bottommost path, so let's say go Shenzhen City to Hong Kong Port to New York City, and then New York City by truck to Kansas City. So what is this journey going to cost me? It's going to be $30 plus $1,200 plus $1,150 is going to be what each container is going to cost me. Okay, so when you trace out a route, add up all the dollar values. How much is it going to cost me in terms of time? Add up all the time values. 5 days plus whatever days the port takes, plus 29 days, plus 3 days at this port, plus 2 days. So that's the total number of days it will take you on average. Okay. So now the question is, how many different paths can I take through this diagram? You could take the bottommost one with this leg, that's 2. You could go this way, that's 3. You could go all the way up, that's 4. There are 4 possible paths in this network diagram. And I didn't look at all the options. There are more options connecting LA and Kansas City and New York and Kansas City. And there may be more options connecting the ports to these cities. You could go to Miami Port, for example. So in reality, your network diagram may be a lot more complicated with a lot more options. Now, sometimes you might say, an option is so bad, obviously, that port is so far, obviously, that I'm not going to consider it. That is fine. You don't have to put every single option there. You only put options you think have a realistic chance of being selected in the network diagram. So we can simplify it and say, okay, there are 4 ways to go from Shenzhen, our supplier, to our Kansas City warehouse, which are reasonable ways. I'm not going to count air transportation or unreasonably expensive ways. And of these 4 ways, this is the total cost per container, and this is the cost in terms of time: 38 days, 34 days, 42 days, 39 days. Okay. The cheapest option is $2,030. Which is takes the longest, but is the cheapest. Shenzhen to Hong Kong to New York by rail to Kansas City. Okay. See, TL is truckload, RR is rail, and then here, I don't know if this. You can look at the previous diagram, see which one is rail, which one is truck. They might just be. Or they might be intermodal. Okay. So we can select which option we want, right? So if you are okay with 42 days, obviously the longer the time, the more inventory cost is going to increase for you. You're going to need more safety stock. It's going to be more pipeline inventory costs, so forth. But if that cost is not very high, you might go for the cheapest option, or you might say, well, this option is the most expensive, but I saved 3 days, so are the saving 3 days worth the difference in the dollar amount, right? So you can do those calculations. Now, one thing we have not factored in all of this, okay, is the variability in transit times, because all of these are averages, right? Everything is an average. So on average, it's going to take 5 days. On average, it's going to take 29 days. Now, what I can tell you is that once the ship is on the ocean and going from port A to port B, it's left this port, it's on the way to the New York port, this time can be relatively reliable if the ship is not hitting other ports. A lot of variability comes in from the port operations, port congestion, things like that, but you can actually look at historical data, figure out how reliable these times are, and then you can calculate a standard deviation to represent how much the times vary. Okay. There are multiple dimensions of reliability. You might look at execution credibility and say, well, does this carrier do what they say they do? That should be high before you select a carrier. Otherwise, they make what's called cut and run, don't load all the containers, ship gets full, they overpromised, and they put you on the next ship, right? Like sometimes you go to the airport and the flight is overbooked, you get bumped to the next flight. The same thing can happen with container ships. Your container gets bumped to the next ship next week or something. Schedule consistency, this is the key one as well, where if they say they're going to be there on a particular date, are they there by that date? What's the variability there? So you want to look at the different carriers, look at their historical performance. Here's some data from a study done at MIT Center for Logistics, where what they're showing you is what does the contract say, what did the time did they promise is on the x-axis, and what time they actually achieved is on the y-axis. So if they promised you 25 days, the blue line would be 25, so they're never achieving 25 days. Usually they're going to 30 days. So they promise 25 and they take 30 days. Okay? So you can look at historical data and look at what's the actual performance versus the promised one, and then you can plan your operations expecting somewhere this is how long they're going to take. Okay? So don't just go to what they're telling you, look at historical data to figure out how long something is going to take. Now when we look at reliability, okay, we have the coefficient of variation, which tells you the percentage. So if something has a time of 100 days and the variability is plus minus 10 days, or the standard deviation is 10 days, then your coefficient of variation is going to be 10% or 0.1. So you have about 10% variability from the mean. So a coefficient of variation of 0.2 means 20% variation, standard deviation around the mean. 0.4 means 40%, and so forth. Look at the ocean transit part. It has very low coefficient of variations compared to the other parts. Okay? So what it's telling you is once a ship has left a port, it's just floating over the oceans. There's not much that goes wrong usually, and it's kind of reliable, but a lot of variation comes in at the ports. And then a significant variation also comes in on the origin side, because the supplier might be late, or the truck loading people had some issue. So a lot of things can go wrong here, and also at the other end. Also, some ports are better than others. Some have better processes, technology than other ports. So you can also think about, okay, which ports do you want to avoid, which ports are good for your transportation option, and which ports you kind of try to get if you can get a route through them. So we'll go back to the same data. Let me show you the picture, and I've added in red the standard deviation. So in the New York port, it takes 3 days on average, and the standard deviation is 1 day. So it could go, because usually most values are going to be within plus minus 3 standard deviations. So most of the time you're going to be between 0 and 6 days, because 3 minus 3 is 0, 3 plus 3 is 6. Right? 3 times 1 is 3. So 3 plus 3 times 1 is 6. 3 minus 3 times 1 is 0. So most of the time you're going to be between 0 and 6 days at this port. Okay? So if you don't know what a standard deviation means, what is a normal distribution, just Google standard deviation, normal distribution, look up some tutorial. You should remember that from a basic stats type of class. If you don't, you can look it up or contact me. I can give you some resources on that. Now, notice what's happening. When I went along a path in this network diagram, I added up the dollars amount. That's how you got this dollar amount here. This is the sum of, the numbers on the board. So that one is the sum of the 35 plus 1100 plus 1100. That gives you 2235. When you go along the path, you add up the days in the black. So 2 days, 20 days, 22, plus 5, 27, plus 11, 38, right? If you go, so that you go on along the top path, right? 22 and 527, yeah. Okay. And so you add up the days, right? So you got the 38 days right here, which is the sum of 2 plus 20 plus 5 plus 11, you get 38. Okay? But look at the red number, 4.8. If you add up the red numbers, 1 plus 2, that's 3, plus 3, that's 6, plus 3, that's 9. Why do I have 4.8 here? It's not 9. So remember this rule. It will help you in a lot of places. This sort of analysis is used in project management. You can represent stages of projects as the nodes and the paths, or the arrows as the project stages and things like that. So use this network diagram to analyze many, many things in management. Okay? Whenever you're using this network type of diagram, always remember this rule: add variances, do not add standard deviations. Okay? So we cannot sum up the standard deviations to get the standard deviation for the total. You have to sum up the variances. So what is a variance? Variance is just a square of a standard deviation. So for this case, I would square up all the numbers. So the 1 day, 1 in red, 1 squared is 1, plus 2 days, 2 squared is 4, so do 2 squared, plus 3 squared, which is 9, plus 3 squared, which is 9. I add all of that up. I take the square root of that, and I get about 4.8. So the standard deviation of the total, 38, is going to be 4.8. This is assuming the standard deviations or the transit times for the different parts are independent. So if your truck is late here on the first leg, that's not going to increase or decrease the probability of the ship being later on time. So one stage doesn't affect the other, which can sometimes be unrealistic. If your truck is late getting to the port authorities might say, we had a time scheduled for you, you're going to be put on the next day now, so you get a delay of an extra day because your truck was late. So the delays may be related. In that case, you have to do a little bit more complex calculation. You can calculate the correlations between the transit times or the delays and build in the correlations into this formula here. Okay, again, you can, I don't cover it for this course, it's a little bit more complicated, but you can easily just ask any statistician or mathematician or engineer with maths background, how do you calculate the standard deviation of the total when your times are correlated? Or you can just do a simple simulation in Excel and get the statistics on the total when the individual components are related to each other, where one goes up, the other tends to be higher. So either way, using the simple formula here or a little bit more complex analysis, you can get a standard deviation of the total. This is the key part, because you can use this standard deviation in two ways. One, it's going to influence your inventory cost. Remember, when lead times vary, you have a standard deviation of a lead time that's going to influence your safety stock is going to be higher. So the more the standard deviation, the more the variability in your lead times, the more safety stock you need. Right? Two, if it's a very high standard deviation, you could sometimes have unexpected delays which are very significant, and that could really hurt your operations. Okay. Now we can ask questions about probabilities. What's the probability that a particular route, will deliver you the product within a certain amount of days? Or which route has the highest probability, to be within 40 days? So you have the average times from the previous slide, right? If you go back, these are the average times: 38, 34, 42, 39. Okay. You have the standard deviation, which was in red in the previous slide. You can calculate a probability assuming this is normally distributed. Why can we assume the total time is normally distributed? Well, if you go back and you look at this total 38 days, we're adding 4 or 5 different times to get the total. Okay, if you add many different things together, the sum is usually going to be normal or normalish distributed by the central limit theorem. The more things you add, the more this is going to be normal. Okay. Now that may not be true if one of the times is very large, like the 20 days is like 40 days, and the others are all very tiny. Then you have one dominant factor, and this may not be normally distributed. Again, you can look at historical data, verify whether the distribution is normal or not. For this course, we're going to always assume distribution is normal. So we're going to assume this time, the transit time, is normally distributed. If you take the first route, the distribution is going to have a mean of 38, standard deviation of 4.8. If you take the second route, the transit time is going to have a mean of 34, standard deviation of 14.6. So depending on which route you take, the mean and standard deviations change, right? Because each route has its own journey, its own times. So I can easily use these two numbers to find the probability in Excel that the transit time is going to be within 40 days. Let's say we care about 40 days. We don't want it to be more than 40 days late. Okay. So you can use the norm.inv function. Value is your threshold value, which in this case is 40 days. Mean is going to be your average value coming from here, this column, and standard deviation is the standard deviation coming from this column. So you put in equals norm.inv 40, 38, 4.8, okay, and then you press enter. It's going to give you a probability of 0.661, which means there's a 66% chance that if you pick the first route, your stuff will arrive within 40 days. Or another way to say that is 66% of the time your goods will arrive within 40 days in the first route, but about 34% of the time they'll take more than 40 days. You can calculate a similar probability for the other routes, and you can see the highest probability of being within 40 days is this one. This is very close. These two are very, very close, but the top two routes give you a higher probability, and the last route here, okay, 39 days, has a less probability, and the cheapest route, look at the cheapest route. This was the cheapest route, which took the longest, I believe. That the probability of being within 40 days is really small, 37%. So more than half the time you're going to take more than 40 days. Even though the average time is only 42, right? You're going to be about 63% of the time outside 40 days. So you can do this sort of analysis to look at the risk, because if it's really important to get something in 40 days, your lowest risk is to go with the first option, because you have the highest chance of making it within 40 days. So these standard deviations help us quantify the risk in terms of arrival times or the transit time for different transportation routes. Okay, so that's it for transportation management part 1, where we looked at intermodal transportation, containers, the inventory implications of choosing a different mode. The same inventory calculation apply to choosing different routes, because as your transit time changes, standard deviation changes, your safety stock, all other inventory stuff is going to change as well. So you have now a total relevant cost basis to look at different routes, look at different modes, and see which one is the cheapest on total relevant cost. The other important factor other than cost is risk. So we looked at how do you get the average transit time for a route, how do you get the standard deviation, how do you get the cost for the route per container, and then you can look at probabilities to kind of quantify the risk of different routes, right? And some of these routes take different modes, because this is truck, this is rail, this is truck plus ocean, this is rail or piggyback plus ocean. So there are different modes built into the routes, right? So you don't have to do it in 2 steps. First look at the modes, then look at the routes. Just build your routes using different modes and just compare them in one go based on inventory cost, transportation cost, the risk factor involved, using these probability calculations. Okay?